Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be completing our discussion on the Buckingham pi theorem. So let me just start the module with a formal statement of the theorem. So the Buckingham pi theorem, it says that this is related to the dimensional analysis of the variables. So it says that if we have a formula, if the formula q is a function of the other variables p1, p2, pn and is dimensionally homogeneous and complete, dimensionally homogeneous and complete, then it is possible to reduce it to the form. It is possible to reduce it to the form q is equal to capital Qf of pi 1, pi 2, pi k. Okay, where pi 1, pi 2, pi k, pi 1, pi 2, pi k are independent dimensionless groups. Independent dimensionless groups and groups of P1, P2, Pn, and Q is also a dimensionless product of P1, P2, Pn with the same dimension as Q. Okay, so this is the most general form of the dimensional analysis in the form of Buckingham pi theorem. Okay, let us look at one more example of the application of this result. This example is coming from a very famous problem in pattern formation, namely the Turing instability. Okay, so the problem says, so we call it as case study 4. This is related to pattern formation or the Turing instability. Okay, so the problem, Turing instability is a mechanism responsible for colorful patterns on butterfly wings. So we must have seen, this is quite a common example. We have seen the stripes of a leopard, black and yellow stripes, and the various colors on the wings of the butterfly. Well, it turns out that there is a general mechanism of these pattern formation on the animal coats. Namely the so-called short-term inhibition and the long-term progression of these chemicals or the colors which are released in the coat. And Turing was the first person who was able to identify this mechanism and formalize it in the form of a set of coupled partial differential equations. Now, the solution is quite complicated. As listeners can clearly understand, we are solving a coupled partial differential equations. But one way to again solve these problems of pattern formation is via dimensional analysis. We will see how. So let me just write. So this is colorful patterns on the butterfly wings, zebra stripes, etc. So experiments developed to study the pattern formation. Let me call this pattern formation as PF. Okay, so developed to study pattern formation involves pouring chemicals in one end of a long tube, and watch the interaction. Okay, so one model which also deals with pattern formation is the so-called Langille-Epstein model. So let us see what the model says. So we are going to just focus our attention on the Langille-Epstein model. So the model says that the patterns, they appear only for certain pouring velocities v. So only when the velocities reach a certain threshold are we going to see the formation of patterns. So patterns appear only for certain velocities, certain pouring velocities v, right? And it turns out that the velocity v depends on the concentration of the chemical, depends on first the concentration of the chemicals u, and second, it also depends on the rate K2 at which the chemicals interact. Okay, and finally, lastly, it also depends on the diffusion coefficient of the model D. And then there is another parameter K3. It also depends on the parameter K3, which is having a dimension of concentration squared. Okay, so we have now, to begin with, the fundamental dimension of velocity is L over T, and then we have, for the concentration U, the fundamental dimension will be 1 over L cube, because this is per unit volume. So, concentration is per unit volume. And similarly, the rate K2, the fundamental dimension of K2 will be this is rate at which the chemicals interact. So this is volume per unit time. So this will have a dimension of L cube over T. Then we have K3. K3 has a dimension. This has a dimension of concentration square. So concentration has a dimension of 1 over L3. So this will have a dimension of 1 over L6. And then finally, the diffusion coefficient D will have a fundamental dimension of L square over T. So now let us start to play around with this dimensional analysis. We set up the fundamental dimension of this velocity. This is equal to U of A times K2 of B times D of C times K3 of D. And we see that if we see what are the fundamental dimensions of each of these quantities. On the left hand side we have the velocity, so Lt minus 1, and this is equal to L minus 3 to the power A, and then we have L cube by T to the power B, and then we have L square T minus 1 C, and we have L6 of D. Right? And then what we have is, if we are going to compare the powers of the dimensions, for L we have the following equation: 3A plus 3b plus 2c minus 6d is equal to 1. On the right hand side, left hand side, it is 1. And for t, we have that minus b minus c is equal to minus 1. And from here, we can quickly find out that b is minus. So we have a, b, c, d, four equations and four unknowns and two equations, which means that we expect two non-dimensional groups, pi 1 and pi 2. So b comes out to be minus 1 plus 3a plus 6d, and c comes out to be 2 minus 3a minus 6d. And from here we can quickly find out the dimensional form of the velocity of pattern formation. So v comes out to be alpha times d square by k2 times the first dimensional group u times k2 cube by d cube to the power a times k2 6k3 by d to the power 6 d, right? And then we can see that this is also equal to alpha k2 minus 1 d square pi 1 a pi 2 b, where my pi 1 is this group u k2 cube by d cube and pi 2 is this group. Okay, so then which means that I can write down the general form. The general form of v is k2 inverse d square times f of pi 1 pi 2, right? And now if we were to solve the Langevin-Epstein model, well, I'm not introducing the model but just giving you the formal answer to this system, and try to compare it with what we have found in dimensional analysis. So solving the Langevin-Epstein model, will provide us with v is equal to square root k2 du g of beta, where my beta is the group, dimensionless group k3 by u square, and what else we have is that now, so this is the formula that we get from the Langevin-Epstein model. It seems if we term these two forms of the velocities as 1 and 2, it seems that 1 is very different than 2, but we will see they are not. So if we were to equate, so what we do is, notice that beta is nothing but pi 2 by pi 1 square. So this is the observation. And now if we were to look at these groups, we see that equating the form 1 and form 2, because they both represent the same quantity, the velocity of the pattern formation. So equating 1 and 2, we find that f of pi 1 pi 2 is square root pi 1 times g of pi 2 by pi 1 square. And notice that again we have found that the equality is only in the form of two dimensionless group pi 1 and pi 2. So it turns out that 1 is identically at least dimensionally identical to 2 because of the fact that f and g are related as follows, right? So that is what it is. Okay, so the conclusion from this exercise is that the result that we find by solving a complicated model of that of Langevin-Epstein is identically equal to the result that we found from a simple dimensional analysis. So the dimensional analysis on one hand has a lot of superiority in terms of its simplicity, but of course there are certain variables. For example, this dimensional constant alpha, which always remains unknown or have to be experimentally found. So that brings us to the end of this topic. Let us now conclude by noting what are the advantages and disadvantages of dimensional analysis. So the conclusion. So what we have is the dimensional reduction. The dimensional reduction has reduced the original function of 4 variables. In this, I'm just talking with respect to the pattern formation example. So 4 variables into 2 variables. And this is a function of f of pi 1 by pi 2. Right? And the second point, but it cannot reduce the function down to one variable, such as the one given by Langevin-Epstein, such a one variable function such as g of beta. Right? And the reduction, it turns out that the reduction from 2 variable to 1 variable requires some knowledge about the inherent model of the system. So the reduction from 2 variable to 1 variable requires information at the modeling level. And in this case we have the Langevin-Epstein model. Okay, so that brings us to the close of this discussion, namely the dimensional reduction of the variables and how it can be used to solve complicated problems. Now, in the next topic, we are going to introduce yet another method of solving the problems in classical mechanics, namely the method of similarity transformation or similarity variables. So let us now introduce this topic. So we are talking about similarity variables. So I'm going to start with some basics which will help us understand as to what we are trying to find. So it turns out that dimensional, to begin with, let us again revisit. The dimensional reduction method is able to solve very complicated mathematical problems, right? So this is, we recall, the dimensional reduction can also simplify complex math problems. Example, the diffusion equation for finding the mass density. The diffusion equation, right? So this is u of x comma t. So let us call this diffusion equation model as 1. So d of uxx is equal to ut. So people familiar with at least some basic partial differential equation knowledge must have seen this equation very often. That is a one-dimensional diffusion equation, and the domain is x is the entire positive real axis, and t is greater than 0. Okay, and then we can further introduce boundary conditions. We have that u at x equal to 0, let us say this is u0, and u at x tending to infinity is 0. Right? And similarly, we can also set up some initial conditions that u at t equal to 0 is 0. So at least This is, we expect the diffusivity or the diffusion coefficient D to be positive, and of course we have that, so diffusion coefficient to be positive. Okay, so then the idea is we want to solve this problem using dimensional analysis, and let us see what happens. So people with the knowledge of PDE must have seen the solution to this equation, and it will be now easy to compare how close the dimensional analysis takes us to the original solution to this problem. So now if we look at, so these are certain facts of dimensional analysis of derivatives. So it turns out, so I am stating some facts here. So it turns out that the dimensional analysis of df dt is the dimension of f divided by the dimension of t, right? And similarly, the dimensional analysis of d2f by dt2 is the dimension of f by the dimension of t square, right? And similarly, if we have to find the dimensional analysis partial u partial x, then this is the dimension of u divided by the dimension of x. And similarly, if we have mixed derivative d2u by dt dx, the dimension of this is equal to the dimension of u divided by the dimension of t divided by the dimension of x. Okay, so then let us come back to the diffusion equation problem again. So we see that so this is the 1D diffusion solution, right? So we are assuming now our diffusion is the solution to the diffusion equation is going to be a function of whatever variables we have, the variables being x, t, d and u naught, right? So now we set up the dimensional analysis. So u is x of a, t of b, d of c and u naught of d, right? And now this is going to be, u is a concentration, so this is going to be mass per unit volume, so this is the concentration. And then the dimensional on the right hand side is going to be La, Tb, L square by T, Tc and L U naught again is a concentration, so this is going to be mass per unit volume of D. And now this is going to be L of A plus 2C minus 3D times T of B minus C times M of D, and again set up the equations for L, T and M. We get 3 equations for 4 unknowns. So these are my 3 equations, and B minus C is equal to 0 and D is equal to 1. So now we see that solving this set of 3 equations and plugging back into our dimensional analysis, we find that U is alpha times U naught times a dimensionless group x over square root dt. X over square root dt to the power a. And now people again, we recall the original solution to the diffusion equation definitely involves this dimensionless groups in the form of an exponential of this group. Again, if you recall the solution of this original PD. So we are very, very close to the solution, except that the exact form of the solution, exact form of this appearance of this group is not known. So, what is now, we now introduce a new name for this non-dimensional group. We call these non-dimensional group as my similarity variables. Similarity variables. Okay. So here let me call this similarity variable as eta. So eta is x over square root dt. So now dimensional analysis have brought us to at least this step where we have some form of the solution. This question now is, can we still move a little bit further to find the form of this dimensional group, the functional form of this dimensional group? That is something we need to explore. And to do that, we will use the method of similarity variables in the next, again using this same example. So what we have found is the following. So for 1D diffusion, the solution is of this form: u of x comma t is u naught times f of eta, where eta is the similarity variable x over square root dt. Right? And now, having solved one set of three equations, we have found this form of the solution. We could have had another solution. So note that we could have another form of the solution possible to derive a different representation, A is equal to minus 2b and c is equal to b, and from here we see that u is u naught g of zeta, where my new similarity variable zeta comes out to be dt by x square. This is again solving the set of three equations for the dimensional analysis, and keeping some other unknowns, we can come to this conclusion where we have another similarity variable, right? So this question now is, let me call this as form 1 and this as form 2. So this question is whether to choose form 1, whether to choose the form 1 or 2 for the final form of my answer. So I am actually going for the kill here. I am trying to find the exact form of the solution to this 1D diffusion equation, this time using the method of similarity variables. So to do that, we have to pin down the fact as to what form of the solution should we choose, because it turns out using dimensional analysis that we could have multiple ways of representing the solution using different similarity variables, as we see here using form 1 or form 2. Now, if we go back to the problem, the diffusion problem, the 1D diffusion equation here involves second derivatives with respect to x, uxx, right? Now, notice that if we had used form 2, then second derivatives would be very problematic, which means that we would have to use multiple chain rules in order to evaluate this second derivative uxx. On the other hand, we see that eta in form 1 is only a linear function of x. So uxx will be relatively easy to evaluate if we use form 1. So the answer to this question lies in the fact that since form 1 has linear x derivative, we have that we use form 1, use 1. Okay, so then we use form 1. So then what we have is that ut is equal to, now we are going to use the form 1 of the solution, and now let us plug this into our original 1D diffusion equation. And now what we get is ut is u naught f prime eta d eta dt. So this is our ut using chain rule is what we have found. So again, this is going to be u naught f prime eta times minus x. So t is in the denominator here with square root. So this is 2 times d to the power half times t to the power 3 by 2. right? And we see that this is also equal to u naught f prime eta times eta over 2t. So eta over 2t. Similarly, if we were to find what is uxx, so uxx comes out to be u naught times f double prime eta times 1 over dt, right? And if we plug both these forms of ut and uxx in the 1D diffusion equation, we are going to get the following new equation, that f double prime eta is going to be negative 1 over 2 eta times f prime eta, right? So now we have got completely a single ordinary differential equation involving just one variable eta, where now so notice that x, originally x is lying between 0 to infinity and t is positive, so which means that now earlier we had, so notice in this ODE, this is a second order ODE in eta, so we need some boundary conditions. In fact we need two conditions on eta because this is second order. We originally had conditions on x and t. From there we can find the condition on eta. So what we have is, notice that we had condition that u at x equal to 0 is u0, right? Now from so what have we got here? So u at x equal to 0 is u0. So if we plug it into this form, the form 1, so we get that this is also equal to u0 times f at, so f at eta at x equal to 0 is 0. So this is f at 0. So from here we see that f at 0, so we get one condition, f at 0 is 1. So at eta equal to 0 the function f is 1. Similarly we have another condition at infinity. So we saw that u at t equal to 0 is 0. That was the condition. But this is from the form 1 is also u naught times f at x over square root dt, and this is when we put the limit t going to 0 plus, right? So when we take t to going to 0 plus, we get that this is also equal to u naught times f at infinity, and this is 0. So from here we get the condition that f at infinity goes to 0, f at eta goes to 0 as eta goes to infinity. So these are my two conditions on etas, and we can very well now solve the ordinary differential ordinary differential equation involving capital F. If we do that, so now, so the problem is f double prime is equal to minus half eta f prime, and eta now is between 0 to infinity, with f of 0 is 1 and f of infinity is 0. And if we solve now, I am not going to solve this and show you the steps, but directly give you the answer that after the solution we see that f of eta comes out to be beta plus alpha times 0 to eta e to the power minus s square by 4 ds. And now if we start plugging in the boundary condition, f of 0 is 1, we see that beta is 1, and if we use f of infinity is 0, we see that alpha comes out to be negative 1 by square root pi. And now if we plug it into this form, we find that f of eta comes out to be 1 minus 2 by square root pi integral 0 to eta by 2 e to the power minus r square dr, or this is also equal to the error function complement of eta by 2, right? And then error function complement of eta by 2, and so my final form of the solution u of x comma t is u naught times error function complement of x by 2 square root dt. So notice that using a combination of dimensional analysis and similarity transformation, we have been able to completely solve this 1D diffusion equation. And the combination of these two methods, namely the dimensional analysis and the similarity transformation, allows us to devise a new method of the solution of these models of classical mechanics. Okay, so of course, so what we have seen through this exercise is similarity transformation is a method of solving complicated partial differential equations. But the limitation of the similarity transformation is that the problems must have a very specific form, right? Not all partial differential equations can be readily solved with this method. So let me write what I just said. So what I said is that the similarity variable is an alternate route of solving complicated partial differential equations. Okay, so solving complex PDE, but the limitation is that the problems must be of specific form. Must be of specific form. So I end my discussion in this module, and in the next module we will be continuing on non-dimensionalization and scaling arguments. So thank you so far for listening.